So sequences and series, again, are usually a topic that is covered supposedly in pre-calc, usually very quickly. Most students often don't remember it very well. So they actually begin when we look at things in 8.1 with an overview of sequences and series. And again, it kind of makes sense because many students have seen it before. But at the same time, my experience has been is that students don't really remember it and don't feel comfortable with it, even if they have seen it before. So it is somewhat good that they're having an overview here to get people's a chance to think about it from scratch. So very briefly, to remind us of how they start, that we want to keep in mind that there is a difference between a sequence and a series, and remember what the two are. And a sequence is written notationally with a set notation and something like a sub k. But that in the end, it's just a list of numbers that are in some particular order. So it could be like 2, 5, 11, 20, 99. And a sequence could be finite. It could just be, as I've written here, 5 different numbers written in an ordering. Or if they put like a dot, dot, dot at the end, that usually suggests that the sequence keeps going and that it's infinite, that it doesn't stop. It's just a long list of numbers. So it could be something simple, like even numbers, 2, 4, 6, 8, 10, 12, off to infinity. Or it could be something like I've written here where it's hard to see what the pattern might be, but that somehow the list just keeps going. So then a series is where you take a sequence and you add everything up in it. You add up all the numbers. And so when we write it notationally, we use the summation notation. So in this case, it would be 2 plus 5 plus 11 plus 20 plus 99, etc. And so this becomes an infinite summation. And then there's this whole question as to whether it converges or diverges. Because as we've seen when we did improper integrals, when you have a total that's being summed up that keeps going and going and going, it could actually settle in on a value, or it might be that it diverges because it doesn't or refuses to settle on a value. So in this beginning section of the chapter, they sort of remind us of this notation. They talk about terminology a little bit, define a sequence. And the first concept that comes up is the limit of a sequence. So we can sort of ask, does the sequence of a sub k's have a limit? So this ends up being an issue kind of like what we did in chapter 2, back in the first semester calculus of limits. And it basically means, does the value of the sequence as you keep going off toward infinity settle in on a number, just like a limit might? So for an example, if I had a sequence where my numbers were k over k plus 1, so I'm using the set notation. I'm putting in the formula for a sub k, and then I would imagine as k starts counting with the first, second, and third terms, when it's a 1, I would have 1/2. When it's a 2, I would have 2/3. When it's a 3, I would have 3/4, etc. So then the question could be, does this sequence have a limit? And what that means is, as I'm going down the sequence and heading off toward infinity, are the terms in the sequence settling in on a value themselves? That eventually, if I went far enough, would it look like the sequence were basically the same number every time in the list of numbers? And to evaluate that, you would take the limit as k goes to infinity of the formula for the terms in the sequence. So that may or may not look like a limit that you're comfortable with at this point. Hopefully it is. So in this case, the limit of this rational expression as k goes to infinity is 1. And so therefore I would say the limit of the sequence converges to 1. Maybe I'll even write that. So converges, to use the right language, to the value 1. All right, so they introduced this terminology. They gave a definition of a limit of a sequence on page 599. So I'm going to write in here, this was definition limit on page 599 for those who are sort of reviewing these sorts of things in anticipation. So then they introduced the idea of adding all of these sequence values up and getting a series, and the idea of an infinite series definition is on page 602. So going back up here. So the definition of infinite series that we're talking about here is on page 602 for reference. And then they had some exercises. So that's sort of the quick overview of what was in 8.1. And since it's sort of the first overview section, I wanted to give that a little bit of mention or review. But let's see if we could then see what kind of problems they wanted us to be able to do based on that review by looking at the exercise set. Okay. Not working. Hang on. Okay, now it seems to be working. Don't know why it wasn't. Okay. So this is on page 604. Exercise. And let's maybe grab let's grab 10. No. Let's go down a little bit further. Let's look at $19. So it says, write the first 4 terms of the sequence defined by the following recurrence relation. So one of the things they talked about in the sequence discussion is the different ways that you can write a sequence. One was with an explicit formula, as I just gave in the example of k over k plus 1. But the other was that you could give a recursive definition, whereas there was a recurrence relationship between the nth plus 1 term and the nth term. And so they're looking at that in problem 19. So in problem 19, it says a sub n plus 1 is defined as being 3 times a sub n gives you a minus 12. And there's a question about how do you turn a recursive definition into an explicit definition. There isn't a straightforward formula way to do that. You'd kind of have to look at each case-by-case basis and figure out how the described transition can be expressed with an explicit formula. You know, for example, if it's something like I'm taking the previous one and multiplying it by 5, well, then your formula is going to be a power on a 5 because every time you multiply by another 5. But if it was something where every time the way I get to the next one is by adding a 7, like an algebraic situation, well, then instead of having a power, I would have to multiply by a 7. How many 7s did I add? I would multiply by 7. So it really depends on the problem. There isn't a specific way to do that, Wenzel. Okay, so they give us this recursive definition, and then they also tell us the first term is a 10. So we know that a sub 1 is equal to 10. And again, the goal in this case was to just list the first 4 terms. Maybe just to follow up with Wenzel's approach, we could also see if we could create a formula for the nth term in general. But let's start with what they wanted. They want a sub 1 and a sub 2 and a sub 3 and a sub 4. So a sub 1 is actually given, it's a 10. So for a sub 2, what the formula says is you take the previous term, multiply it by 3, and then subtract 12. So if the previous term was a 10, if I multiply that, what I would get here is I would get 3 times the previous 10, which is 10 minus 12. And if I do that little arithmetic problem, I get 18. Then to get a sub 3, that would be 3 times the previous answer, which was a sub 2, or 18, minus 12. So that's what, 54 minus 12, I'm getting like 42. And then a sub 4 would be 3 times what a sub 3 was, minus 12. So that's like, well, what? 126 minus 12, which would be something like 114, unless I made a little arithmetic mistake there. So we're asked for the values of the first 4 terms. So we have a 10, an 18, a 42, and a 114 as our first 4 values. So this is the idea of using the recursive definition. So now, Wenzel, do you think you could turn this into an explicit formula? Could we, from this idea, figure out what is a sub k? Well, that's a good challenge, right? What do you think, Wenzel? As you can see, it really kind of depends on the arithmetic of each problem individually. Sometimes it's not a straightforward way, but usually there should be some way to do it. Thoughts, suggestions, comments about coming up with an a sub k formula? So the problem is that each iteration of the step in the sequence of terms has 2 operations take place. You not only multiply by 3, but you then subtract 12. So how do you iterate that with a formula? Well, you could, and then you have to do both of those before you do the next iteration. So I don't think there's a real nice, clear way to do this. I'm sure there's something that might come up with a formula, but I'd have to think about it and play with it. I think this is a good example that in general, there isn't an overall way to do this for all problems because it often can be kind of complicated. If I was just multiplying by 3 each time, that would be easy. That'd be a geometric formula. If I was just subtracting 12 each time, that would be easy. That would be an arithmetic progression. But when you do the 2 of them and you have to do both before you can do the next one, it gets complicated. And so this is a good example to show that there isn't a formulaic way to do that. And that's also a good reason why we have a recursive definition as an alternative. But that's all they wanted in this case. So let's plot that on the sideboard because our time is pressed today. And it might be that if we play with it algebraically, we could come up with a formula, but not the best use of our time at this point. So instead, let's try to look at another example. And let's see, bump down a little bit further down. So let's maybe look at something with the limit of a sequence. So let's say we look at, I don't know, how about 33? Got to try to keep things moving because in my morning session, I ended up with only 20 minutes to go over chapter 9, which was not fun. I'm going to see if we have more time at the end of today. So we have lots to cover. 33, again, this is on page 605. And so on 33, it gives us a formula for a sub n. It's equal to 1 over 10 to the n. And this is where n is equal to 1, 2, 3, etc. So that means this is an infinite sequence. And the instructions are, write the first 4 terms of the sequence. If it appears to converge, make a conjecture about its limit. If the sequence diverges, explain why. So remember, we are back in 8.1, so we hadn't defined a geometric series or sequence or any of that stuff. And I put my n a little funny here. That's supposed to be 10 to the power of n, and I made it like a subscript. I was just writing too fast. So let's fix that. Oops. So yeah, so on this point, they're just having us sort of make a conjecture when, as you may recall from, I think even in 8 point, pretty quickly, we can figure out whether this is a geometric series and when it converges and things like that. So, but first it says to write out the first 4 terms. So when n is a 1, we have 1 over 10. When n is a 2, we have 10 squared in the bottom. When n is a 3, we have 10 cubed in the bottom. When n is a 4, we have 1 over 10,000. And so there's the first 4 terms that they requested in the problem. And so then it says, do we think this sequence converges? And to make a conjecture about its limit if it does, or explain if it diverges. So again, to do that, we would want to consider the limit, in this case, as n goes to infinity of the terms themselves. So what does this limit evaluate to? Just to get your brains back in the mindset of a limit. Anybody want to offer it up? 0, absolutely. Because that's a limit that we can evaluate. And so in this case, we say, yes, this sequence converges to 0. So we can say that it does converge and even provide the value that it converges to. So anyway, there's a couple of problems from 8.1 before we had gotten very far into this idea of sequences and series. Questions, comments, or discussions? Yeah.
So in the original problem that you just gave us, it says explain why if it converges. Oh no, it said explain why if it diverges.
Yeah, that was if it diverged, but we can look at that if you want to, if that explanation.
Okay, if it diverges, can you just give me an example of an explanation?
Yeah, so let's say we just flipped this. So then we would be considering the limit as n goes to infinity of 10 to the n. And how do we feel about that?
Right, so that would diverge because the limit would be infinity, so there is no limit.
Yeah, and that's a perfectly good justification because it kind of depends on the language that you're using because the limit is infinity. So what does that mean? So you could try to explain it a little better, but actually what you just said would be fine with me. But let me just to try to be clear the concepts behind, because they're based on earlier concepts of limits. Diverges because the term values grow without bound and never settle or converge to a limit value. So when you say the limit goes to infinity, you're basically saying this. But it doesn't sound like an explanation. It just sounds like you're giving some other definition to describe your answer to this problem. And they're both valid, but sometimes the concept gets lost along the way. So how do you feel about that?
No, yeah, that's fine. Thank you.
Okay. Yeah, so in section 1, they're not looking for anything too deep. They're really more wanting you to feel that you understand the possibilities and the whole idea about the terms of a limit converging or not. Okay, so let's go on to A2. So we just did an overview of sequences in series. So then in A2, it's just about sequences. So if it's just about sequences and they just introduce sequences, what do they do in A2? They get a little bit more formal and they give us some formulas for some specific things. So they do start with a couple of theorems about the limits of sequences. Theorem 8.1, I don't want to go into too much detail because they're ideas that just give you tools to do problems, which we'll do next. But in Theorem 0.1, it basically says if you can express the terms of the sequence using a function, and you can evaluate the limit of the function as you go to infinity, then that's the same as the limit as the sequence goes to infinity. In 8.2, they basically use some of our limit properties from chapter 2 about limits for functions and apply them to limits of sequences. So if you have a sequence that is the sum of two other sequences, then the limit of the sum sequence is the sum of the sequence's limits. I know it sounds like a word salad at that point, but that was Theorem 8.2. It basically does what allows you to do what you think you can do. You can use the distributive property over summation for limits for sequences. So the real new stuff starts with the definitions, which I'm not going to write them all up here, but let's remind us that there was a box that had a half dozen definitions on it on page 608. And these are definitions that are important. And so instead of writing them out, I'll remind us the words that, some of the words that were defined there. So for example, increasing, or more subtly, non-decreasing. And then of course that meant you could do decreasing and non-increasing. And then we had monotonic and bounded. And bounded. So there's those half a dozen definitions on page 608. And these were used for us to be able to talk about the behavior of a sequence. And so that we could use that language to draw conclusions and discuss things. So one of the most important things, or that's a theory idea behind this, was Theorem 8.5 on page 612, which was short and sweet, so I'll just write it down. A bounded monotonic, left out some letters there. Monotonic sequence converges. So if it's only going up, but it has a limit, or if it's only decreasing and it's still bound below, it has to converge to some number. And so that's a theory question that's sort of used a little bit in a couple of problems. They talk about growth rates. And they even give everyone's favorite, the epsilon delta definition of a limit of a sequence, which is like the epsilon delta definition of a limit in general. But let's look at a couple of examples of what they expect you to be able to do from this. So looking at page 616, the exercise set for 8.2.
So that says 8.3 or 8.5.
I'm sorry?
When it says Theorem 8.5, is that 8.5 or 8.3?
Oh, maybe I copied it wrong. It is 8.5.
All right, thank you.
Yeah, there was 8.3 was a reminder of a geometric sequence. So they introduced geometric sequences. 8.4 was the squeeze theorem, which we didn't use too much. So I'm not going to try to rewrite or go over every theorem just because we will have even less time than we currently have if I do that. But I'm just kind of pointing at some of the key ones and what they were used at the time. So the 8.5 is important because it uses those definitions that were introduced, the half a dozen definitions introduced before. Yep. So that was 8.5 on page 612. But anyway, so let's look at an example and see if we put ourselves in a position where maybe we can do something with this. So how about number, how about 11? So this is in the exercise set for the section as an example of the kind of things they want you to be able to do. So it says, find the limit of the following sequences or determine that the limit does not exist. So in 11, the sequence is set notation and they give a formula for it. It's 3n to the third minus 1. Oh, there you go. Minus 1 over 2n to the third plus 1, I think. Yeah, lose my place. And again, find the limit or say if it diverges. So as I was mentioning, this puts us in a position where we're trying to evaluate the limit as n goes to infinity of the formula for the function, 3n cubed minus 1 over 2n cubed plus 1. And so one of the theorems that we had said that if there's a function that produces the values of the terms of the sequence, then you can evaluate the limit of the function to evaluate the limit of the sequence. That's a theory idea. Basically, it means it allows us to evaluate this limit like we would if it was a chapter 2 problem and this was a function. And so can anybody remember what we would get by looking at this problem if we were to just evaluate this limit as if it was a normal function? So Jack is suggesting we get 3/2. That's exactly right. Yep, lots of people coming up. So this is a rational expression. And the idea was that you look at the leading power terms of the polynomial on the top and the bottom. And if the bottom or the top has a higher degree than the other, then that will dominate. But if the degree matches, as in this case, then they balance out perfectly. And you then just look at the leading coefficients of those powers. And that allows us to conclude that this limit would be 3/2, as several of you correctly pointed out. Okay, so in this case, we found the limit. So in some sense, we are just reminding ourselves of some limit skills from chapter 2 and being able to evaluate limits. But we're doing it in the context of also trying to recognize that this is a sequence. So just to be clear, just to remind ourselves, because what we just did looks like stuff we did a long time ago. What is this sequence? I would plug in numbers for n and see what I get. So if I plug in a 1, I would get what? 2 over 3, I think. And if I plug in a 2, I get something worse, like 2 cubed is 8, 24 minus 1 is 23, and on the bottom I would get 17. Anyway, so that you're getting these numbers, but what this result tells us is that eventually it starts to look like 3/2, 3/2, 3/2. It won't be exactly, but that all the numbers after a while are settling in on this value and getting closer and closer to that value, infinitely close as you go infinitely far down the list. So that's what that result means in the context of a limit of a sequence. Questions, comments, discussions about that? All right, so they did also introduce geometric sequences, meaning where you arrive at the next number by multiplying by some constant R value each time. And so let's maybe grab a problem to remind us of how that worked, if I can find one. Determine whether the following sequences converge or diverge, state whether they're monotonic. So maybe let's look at 45. Change color. So if I look at exercise 45, again, this is on page 616, and this is from 8.2. It gives us a sequence of 0.2 to the n. So they're giving a formula for an infinite sequence, and we're supposed to figure out whether it converges or diverges, and whether it's monotonic or whether it oscillates. So here's our choices: converge or diverge, monotonic or oscillate. Okay. So we might start out by trying to remind ourselves, what does this look like? So this is 0.2. Then I would square that and get 0.04. And then I would cube 0.2 and get 0.008, etc. So this is a sequence of numbers, sequence of terms. And in this case, we have what's referred to as a geometric sequence. So they gave us a little theorem in there that basically said if the number you're multiplying by each time, so I'm going to write this as geometric with the multiplying number each time, which we use R, meaning for the consistent ratio of 0.2. If the R number you're multiplying by each time in a geometric sequence is less than 1, then it converges. So we can say, therefore, converges, and specifically it converges to 0. Anytime you keep multiplying by something less than 1, and that's the only way you change the number, then it's going to shrink away to nothing. So this would allow us to conclude that it's a convergent sequence. Then we're supposed to determine if it's monotonic or if it's oscillating. So monotonic can happen one of two ways. That's that half a dozen definitions we referred to earlier. It can either be monotonically increasing or monotonically decreasing. And what that means is that if it's going in that direction, it never changes. If it's decreasing, it just keeps going down and down and down and down and never turns around and goes up, or never even pauses. If it's increasing, it goes up and up and up and up and never descends. So these values keep getting smaller and smaller and smaller as they converge to 0. So in this case, they are decreasing every time, being less than they were the time before. And so we conclude that this is monotonic. So this is a convergent sequence, which is monotonic and converges to 0. So it's possible that it converged to 0 without being monotonic. So that's certainly a possibility. But in this case, it's monotonic. So just for comparative purposes, if I changed this problem a little bit, so let's say instead that this was negative 0.2 to the nth power, then the first one would be negative, then the second one, because it was squared, would be positive, then the third one would be negative. So if that was the case, then it would still be going to 0, and I would still say that the terms converged. But because it's oscillating between positives and negatives, then it would decrease when it from a positive to a negative, but then it would increase when it went from the negative back up to the positive. So in that case, it would be an oscillating sequence that converged. So there's a sort of the example in the book in which we were given 0.2 to the n, and we concluded that it converged and that it was monotonically decreasing. And then I modified it a little bit, put a minus sign on it, and then showed that you could have it converging to 0 even though it oscillates. And these are both, in both cases, these are geometric sequences. So in the case for the minus, then I'm multiplying by negative 0.2 every time. And again, this is still has an absolute value less than 1, and so it still converges. I should put absolute value. Questions, comments, discussions about these examples from 8.2? Okay, let the fun continue. Okay, so then in 8.3, they go back to series. And again, series are where you have a sequence that goes off, but you add all the terms up, and then you get a summation, and that produces a series from the sequence of values that you had. So pretty quickly with the, first of all, the title of this section is Infinite Series. But they start out pretty quickly by looking at a geometric series. So again, what is a geometric series? It's a series of a geometric sequence. So they introduced the idea of a geometric sequence in 8.2, and now they're extending that to a series. And so just to remind us, you could have infinite or you could have finite. And so quick example, if I have a sub n equal 1 over 2 to the n, and I add those up, I have the series of a sub n's. That would equal like 1/2 plus 1/4 plus 1/8, etc. So this would be an example of a geometric sequence. And if I add the terms up and let it go off to infinity, then I get an infinite geometric series. But you could have a finite geometric series as well, even though the title of the section is Infinite Series. They do discuss briefly that it could be finite. So let's do this. If I stopped after the third one here, if this is, I'm still using this as my description of my sequence terms, but if I stop after the third one, then I would write that by saying as n goes from 1 to 3, and then I would just get the first 3 terms. So this is an example of a finite geometric series because the terms form a geometric sequence, but I'm only adding up a finite number of those terms. And then when we have that, there's a formula for the total. And they spend a little time getting it, but they give it to you pretty quickly. So it's the value of the first term. And they don't seem to put the sub 1 in the book, but I'm just going to keep it there so we remember that's the first term. Times the fraction of 1 minus r to the n over 1 minus r. And so we could do it in this silly little example here. If I was trying to do this 3-term geometric sequence above, series above, then this would be the first term is 1/2. And I would multiply that by 1 minus 1/2, where the 2 is to the 3rd power, divided by 1 minus 1/2. Whatever that comes out to be. I think that comes out to be like 7/8. If I'm doing my math quickly and correctly, it's just some number. So, but nonetheless, we have a formula for the sum of a finite geometric series. And so then what they do is they say, okay, well, what if we don't stop at a particular point and we just keep going out to infinity? So then if we did this off to infinity, if I instead said, okay, now let's take the infinite series, meaning we're going to let n go from 1 to infinity of a sub n. So then we get the 1/2 plus 1/4 plus 1/8. And at that point, I'm at 7/8, but we don't stop there. We just keep going and adding more and more and more and more. Then we have an infinite geometric series. And the formula for that is very important because we use it a lot. And basically, it's the exact same formula above, but you just let n go to infinity because it does. And what we found is that this will converge to a number when the absolute value of r is less than 1, and diverge when the absolute value of r is greater than or equal to 1. But when r is less than 1 and you raise it to the nth power that goes to infinity, that means that this term here would go to 0. So you get the exact same formula above, but that term just drops out so that you get the the sum of an infinite geometric series is the first term over 1 minus r. Okay, so they introduced those, and this second result here is actually a theorem. So let's put that this is Theorem 8.7. On page 621, not only this formula, but this part over here as well, that it converges when r is less than 1 and diverges when r is greater than or equal to 1, absolute value-wise. So this is probably the biggest and most important results for 8.2. I'm sorry that we're in 8.3. In 8.3 for infinite series. And they look at a couple of examples, and they also look at a telescoping series as another possible example. And then they have some fun exercises. So let's try to look at what they expect of you in the exercise set, having gone over this introduction of series, infinite series, geometric series. So I'm looking at page 623. Exercises for 8.3. So let's try 16. So it says evaluate each geometric sum. So we just have 4 fractions here, so we could just add these up ourselves. But the idea is we start simple, possibly even with problems that you wouldn't need the new highfalutin math that we're talking about to do, that you could just do back in pre-algebra. But we want to look at them in terms of our higher concepts. So we would like to recognize that this is a geometric series that's finite. And the number you're multiplying by each time is 2/3. So basically I would say geometric, and I'm going to put finite here, finite geometric series with a sub 1 equal to 1 and r equal to 2/3. And n, meaning since it's finite, equal to 4, because there's 4 terms in the series. So then I would use my formula. I would use a sub 1 is 1 times 1 minus the r value to the nth power over 1 minus the r value. So I don't know what this gives us. Some number. Let's go ahead and take it a little further. 1 minus 16 over 81. Divided by 1/3. So that means that dividing by 1/3 is the same as multiplying by 3, and 1 minus 16 over 81 is 65 over 81. And I could divide the 3 into the 81, so then this reduces to 65 over 27. Anyway, so we have a formula for the finite sum of a finite geometric series, and once we plug into the formula, we can evaluate either directly or on a calculator or whatever. Now, with only 4 terms, it really isn't a big benefit to have been able to get the answer this way versus just getting a common denominator. But what if we had a lot more terms? What if there was 100 terms? I'd rather use a little formula for what I get for the 100th term than having to try to add up all those 100 terms. But anyway, that's a little example. Let's take a look at another one down on the list here somewhere. So let's say we look at, the next batch says evaluate each geometric series or state that it diverges. So let's look at 23. So here they don't give us a formula, they just give us the first 4 terms with a pattern. So it says 1 plus 1.01 plus 1.01 squared plus 1.01 cubed, and this goes on forever. So we want to evaluate or state that it diverges. Evaluate meaning determine the value of the series, or if it doesn't have a value, then state that it diverges. So does anybody have an opinion? It's like a couple people think it diverges. Anybody else, or does anybody want to ask a question if they're confused? Okay, so yes, correct, it diverges. And we have a theorem, if we want to refer to something, Theorem 8.7 that we just mentioned a second ago where you got the formula. But basically, since we have a geometric series with the R value, we're multiplying by each time being 1.01. And since that's greater than 1, it diverges. You can just look at the terms themselves. They're bigger than 1 and getting bigger, meaning they're just staying larger than 1. So if you have terms that are not going to 0, then it's going to diverge. You can even think in advance a little bit, because we have done all of chapter 8 at this point. It's kind of like the divergence test would kind of tell you that. But nonetheless, we can just see it here because since the R value is bigger than 1, it diverges by Theorem 8.7. Which says when you have a geometric series, if R is bigger, absolute value of R is bigger than 1, it diverges, or equal to 1, it diverges. But if absolute value of R is less than 1, it converges, and it gives you a formula for coming up with the answer. Okay, so let's try maybe one more. Don't want to dally too long. The next one, 24, let's look at that. For comparison, same page, it has 1 plus 1 over pi plus 1 over pi squared, pi cubed, etc. Again, the instructions are to evaluate or say that it diverges, meaning evaluate meaning determine the value. So since we are only being given geometric series, if it converges, they want to know what it converges to because we have a formula. So I'll give you a few seconds. Anybody have an opinion, or even if you think it converges, figure out what the answer is? So Jack thinks it converges. Wenzel 2, so that would suggest that R is less than 1. Exactly right, Dima. Exactly. So what is our R value here? So our R value is equal to 1 over pi, right? Which is less than 1. And if we know our R value and we know a sub 1, which is just the first term of the list, then we can calculate the result with our little formula. Pi over pi minus 1, exactly right, Wenzel. So how we get that? So the formula is a sub 1 times 1 over 1 minus R. Simple as that. So in this case, that would be 1 times 1 over 1 minus 1 over pi, because that's our R value. That was not written very well, but so we get 1 over 1 minus 1 over pi. You should simplify this because this is a complex fraction, a big fraction with a little fraction in it, and we simplify that by multiplying the top and the bottom by the LCD of any baby fractions. And if I multiply that, I get a pi in the top, and I get pi minus 1 on the bottom, which is exactly what Wenzel typed in there. Perfect. Okay, so we did 3 problems from this exercise set from 8.3, sort of in the middle area. Of course, there are worse ones, but we're going to keep going. So basically in 8.1 through 8.3, they remind us of and define sequences, series, specifically looking at geometric sequences and series, and mainly focus on the idea of infinite series and the idea as to whether they converge or not. And if they're geometric, not only can you figure out if they converge, but you can figure out where they converge to. But as I mentioned early on in this chapter, we pretty quickly get to the point, and it was right now in the middle of chapter 8, where we're no longer going to worry about what a series converges to. We're just going to be focusing on determining whether it converges or not, meaning converge or diverge. And that if they do converge to a value, figuring out that value itself becomes overly complicated using what ends up being remainder theorems and things like that, but that instead that in modern days that's sort of determined numerically. Once you know it's a convergent series and you can could use it to converge to a number, then you can just go out for the first few dozen terms on a calculator and you'll get all the accuracy for whatever value it converges to that you want. The question is, does it converge or not? So at this point forward in our work, we're really focusing on converge or diverge. And that when looking at series, we start to develop tests to determine whether a series converges or diverges. And we begin accumulating those tests in 8.4. So that in 8.1, 8.2, and 8.3, we set all of this work up. We set up this idea. Then in 8.4, 8.5, and 8.6, for the second half of the chapter, it's all about converge or diverge. So for us, let's look at 8.4, and we're going to start to accumulate these tests. I'm going to leave this up here. So in 8.4, what do? We start with the divergence test. And this was on page 627. And it basically says, just to remind us, that if the limit of a sub k is not 0, then the series of a sub k diverges. So it says that if you have a series and the terms themselves are not in a sequence where the terms go to 0, well, then when you add them all up, there's no way you can settle in on a value. You have to diverge. It doesn't mean you go to infinity, but you can't get infinitely close and settle in on a number if the terms that you keep adding every time in the series aren't shrinking away to nothing. If they're maintaining some non-zero value, then every time you add that, you get something different. It changes all the time. So the limit, if the limit of the terms is not 0, then you get divergence. Now, we have to be clear, this is just a one-way implication. It does not mean that if the terms do go to 0, then it converges. We don't know that. So note, if the limit of the a sub k's is equal to 0, we still don't know. Converge or diverge. So example, and we had some two quintessential examples to illustrate this point that you always want to keep in mind. So you could have a nice simple thing like 1/2 plus 1/4 plus 1/8, etc. So this is a geometric series where you're adding powers of 1/2 each time. You're multiplying by 1/2 every time. And as you may or may not recall, this equals 1. And you could use the little formula for the geometric sequence to tell you that. I'm sorry, for the geometric series to tell you that. But then compare that to, actually, let's put a 1 here, just so the comparison looks nice. Change my answer to a 2 over here. So compare that instead to 1 plus 1/2, starting the same way. But instead of making powers of 2 on the bottom, we just make the power k on the bottom. 1/3 plus 1/4, etc. And so this, where you just have the formula as 1 over k, and you let k be 1 to infinity, we figured out and looked at this a couple of ways to determine that this diverges. I missed a question earlier in the text. I apologize. That's from Nassim. You said, how did we find the R value? Was that for the, Nassim, was that for the 1 over pi example? 1 over pi squared, that thing? You still willing to address that? Because I can address it for you. Nassim, are you still paying attention? I just am trying to respond to your question that I didn't see until now in the text chat. Okay, well, hopefully you didn't go away because I didn't answer your question. All right. Anyway, if you come back and you want to ask, let me know. All right, so I want to look at these two quintessential examples because notice in both of these, the limit of the terms go to 0, but one of them converges and the other, as it states, diverges. So if the limit goes to 0, we still don't know if a series converges or diverges because both possibilities are still true. The fact that the terms go to 0 is not enough to tell us convergence or divergence. So what the divergence test tells us is that you have to have the terms go to 0 just to have a chance for convergence. But that if they do not go to 0, then there's no possibility other than divergence. So that's what the divergence test was all about. Very, very key. Okay. So having sort of reminded us of that test and reminded us of the harmonic series, oh, that's what this one, this is the harmonic series, just to remind ourselves. This gets a name, it's so important. So when you just have 1 over k, the series of 1 over k that I listed as the second example, that's called the harmonic series because it's very, very important. Okay, that was not clearing. Okay, I'm going to try to leave up and accumulate some tests, which means some sloppy erasing from time to time. Okay, so that was the divergence test. And we cannot go into this much detail in every test or we'll run out of time or be able to do no examples. But so let's write out at least what else showed up in here. So that we had 2 more tests in 8.4. The next one was the, there we go, the integral test. So the integral test was helpful because it pulled upon some work we did in chapter 7. So it basically said, if you have a function and your a sub k's in your series can be expressed as a formula function where you plug in k to see what you get, and f is positive, I think continuous, basic, a couple of expectations about f which are normal, then the series of the a sub k's and the integral, the improper integral from 1 to infinity of this function you're using to express the a sub k's, those converge or diverge together. So why was this helpful? This was helpful because it means all of the work we did with improper integrals in 7.8, where we were determining whether integrals converged or diverged, these little infinite tailed area problems, we can apply that to series as well. And you may or may not recall that there was something called a p-series that came from that, where we were able to determine whether the area under functions converged or not based on powers of power functions. But there are other functions too that you could use, and then you can determine convergence or divergence using the integral test. And so we'll take a look at that in a second. But the integral test and convergence or divergence of improper integrals immediately leads us to our last test of the section. So then we'll accumulate these and consider them together. And that was the p-series. And the basic idea with the p-series is that if you have something of the form 1 over k to the p, so it's a power function, p for power, then this will converge if p is greater than 1 and diverge if p is less than or equal to 1. So the key core examples to think about for this, and then we'll do some example problems, is that if I have the summation of 1 over k squared, that this converges. And if I have the summation of 1 over k, then this diverges because p, the unwritten power there on the k is a 1, and if p is equal to 1 or less than that, it diverges. And maybe just to sort of show this extension a little bit, the summation of 1 over k to the 1/2 power diverges. But the borderline between convergent and divergent happens when there's an unwritten 1 on the k. And remember, that's the harmonic series. The harmonic series is the borderline of the power series where you go from series that converge to go to series that diverge. And that happens when p, instead of being bigger than 1, becomes less than or equal to 1. And you may recall that we basically drew those same conclusions when we were doing an improper integral of similar functions back in 7.8. Okay, so that's what these 3 tests were about. So let's look at some example exercises from the set of what they expect us to be able to do with these tests that they've given us. And then in 8.4, we'll do more tests and look at other examples. So let's accumulate these tests on the top. So if I look at the exercise set, I'm saying problem to illustrate these ideas a little bit. So let's maybe grab let's grab 12. I think I used that one before. It looks like a good one. I think that's what I did. So I'm looking at page 638, exercise number 12. And it has summation of k squared over 2 to the k. So what are the instructions? It says, use the divergence test to determine whether the following series diverge or state that the test is inconclusive. Remember, the test only says if the terms don't go to 0, it diverges. Otherwise, we don't know. So that's all they're asking for us to do in this case. Apply the divergence test. So I'm going to mute this for 60 seconds to force myself to shut up and let you guys think about it. Try it. So we have a couple of folks who've chimed in with their thoughts, and we have a limit is 0, so inconclusive, which is exactly right. So again, to apply the divergence test, we're basically saying, I wonder if the terms go to 0 or not. If not, I know it diverges. If they do go to 0, I still have to figure it out. So we would be considering the limit as k goes to infinity of k squared over 2 to the k. So I have been recommending as much as possible that students try to develop almost an intuition about these kinds of things. And so it might be possible that you could draw a conclusion about this with some intuition. So for example, my suggestions before were to take note of the fact, and we did have problems that focused on this, that an exponential function like 2 to the k grows large much more rapidly than a power function like k squared. And therefore, since the denominator is growing big so much faster than the numerator, it will end up causing the ratio to shrink away to nothing and equal 0. So that's sort of an intuition look at this. We also had some definitions about rates of growth of functions that would allow us to conclude the same thing. But instead of going through that process, we might also just ask ourselves, could I evaluate this limit? So how would we evaluate this limit? Any suggestions about how that might be done? So Wenzel suggesting L'Hopital, that's exactly right. So this goes back to Calc 1 problem of a limit. We'd use L'Hopital's rule. Basically, if you have something of the form infinity over infinity, so you could differentiate the top and the bottom. And if you did that twice, then you'll see that you get something that goes to 0. Just a real quick write-up of that. So this is of the form infinity over infinity. So therefore, we can use L'Hopital's rule. L'Hopital, French guy. So that means we can differentiate the top and the bottom, and then we would be evaluating the limit as k goes to infinity of 2k is the derivative of the top, and ln of 2 times 2 to the k is the derivative of the bottom. And so we still have an infinity over infinity, so we would do it again. And we'd get the limit as k goes to infinity of 2 over ln of 2 squared, still times 2 to the k. So now there's no k in the top and the bottom anymore. So instead of the top going to infinity, only the bottom is going to infinity. And that means that the result is 1 over infinity-ish, or 0. So since the limit of the terms of the series is 0, then the divergence test fails to provide us a result, as the people have stated, is inconclusive. So that means we still don't know by the divergence test if this converges or not. Now, pushing the idea a little further about intuition, we now know that this test is inconclusive, but what does your intuition tell you? Is anybody willing to imagine making a guess as to whether this converges or not? Even though we now know that the terms go to 0, it still might diverge like the harmonic series, or it might converge like a geometric series. Any thoughts about whether this converges. Jack thinks it converges. Converges because monotonic. So that's a good suggestion, Dima. I think you're thinking about the theorem where if you have a monotonic and bounded, you get convergence. But that is for a sequence, not for a series. So meaning we wouldn't be able to look at the terms themselves. That would just tell us that we already know the terms converge to 0 because we just took the limit. In order to determine if the series converges, we would have to look at the partial sums, and we would have to somehow convince somebody that the partial sums are monotonic and bounded before we could use that fact of being monotonic to help us draw a conclusion about convergence. So I know that was kind of complicated, but I think you're thinking about a theorem that we had that had to do with sequences that we don't usually use with series because it doesn't usually make things easier, it makes things harder. It's absolutely true, but it doesn't usually apply in cases like this. That was a good try. So in this case, all they asked us to do was to apply the divergence test, which we did. But we can actually figure out if this converges or not. So Jack, did you have any specific reason to believe it converged, or was that your intuition, or what? Well, it's a very good intuition, and I recommend you really try to develop that, because in the end, we, as you may recall, to use tests well, sometimes an intuition is a guiding force to help you choose one test over another. Yeah, it gets large very fast. Yeah, the bottom is just going to grow to infinity much faster than the top. So that's a good intuition to have. But I'm going to point out that we can actually support the fact that this converges with the test, just not the ones we had so far. So I'm going to use this as a segue into the next test, which is the number one test we usually want to use. Yes, Wenzel, that's correct, the ratio test. So if you have a problem like this and you're really trying to test whether it converges or diverges, since the divergence test is of no help, the ratio test is the perfect one to use here. So let's remind ourselves what that looks like. The ratio test is the first test we would have in the next section in 8.5. So this is a segue into 8.5 that asks us how, gives us a way to determine if it converges or not based on the ratio of successive terms. So the ratio test was where you take the limit as k goes to infinity of the nth plus 1 term over the nth term, and you call this result R. And if you take the limit of this ratio of successive terms, if you get something less than 1, then the series converges. If you get something bigger than 1, then the series diverges. And if you get something equal to 1, then the ratio test is of no help. Just like the divergence test was just of no help to us. So what would that mean in this case? We would take the limit as k goes to infinity. Yeah. So the n plus 1th term, I would plug in n plus 1 to both of these. So that would be n plus 1. Sorry, that's supposed to be k. K plus 1 squared over 2 to the k plus 1. And let me fix that over there too, because I can't help myself. Instead of n. Okay, and then we would divide that by a sub k, which is what's originally given. But if you're dividing by a fraction, you can multiply by the reciprocal. So I would multiply that by 2 to the k over k squared. So this would be applying the ratio test, trying to come up with this R value to see if this converges or diverges. So if I rewrite this limit a little bit to make it easier, I get the limit as k goes to infinity. So I'm just going to reorganize. So I have the k plus 1 squared in the top over the k squared in the bottom, and then multiply that by 2 to the k in the top over 2 to the k plus 1 in the bottom. So if I reorganize like that, I can then simplify. So on the right, I have 2 to the k divided by 2 to the k plus 1. That's like 2 to the 5th over 2 to the 6th, or 2 to the 10th over 2 to the 11th. Basically, all the 2's in the top cancel out, reducing the 2's in the bottom to just have 1 left. So I would end up with 1 over 2. Or you could use the subtraction of the powers to see you'd have 2 to the 1 in the bottom. Now, this left part over here, I'm going to recognize that I can write this as k plus 1 all over k squared. And a limit of a product is the product of the limits. The one on the right is just a 1/2. And the limit of k plus 1 over k squared as k goes to infinity is 1. So this just becomes 1 times 1/2, which is 1/2. Pause and see if there are questions about the evaluation of that limit for the ratio test. Well, in the ratio test, once you get that R value, if it's less than 1, you get convergent. So since this is less than 1, then we can say converges by the ratio test, giving confirmation to Jack's intuition. Okay, so we have an example where first we tried the divergence test and it was of no help. And so then we tried the ratio test and we were able to see that it does actually converge by the ratio test. So what I'm going to do is erase all of this and add the ratio test as we move into 8.5 and the tests that we get in 8.5. And I think I'm just going to write those down and then we'll do some sample problems. Yeah. Okay, so we just gave an example that showed in 8.5 we got the ratio test. We're accumulating tests. And they actually give the ratio test as a theorem on page 641. So just to make a little note temporarily, this was on page 641 was Theorem 8.14 was the ratio test. So then the next one is Theorem 8.15 is the root test. So let's add that to the list of tests that we're starting to accumulate. Then we have a comparison test. Then we have the limit comparison test. Yeah, we moved into 8.5 as soon as we went to the ratio test. And then I'll hold off on the alternating series test because we have to do some definitions and stuff before we talk about 8.6. But anyway, so these are all of our main tests that we get in 8.4 and 8.5, just to put the list up. So just for clarity, these first three were in 8.4 for up here, and then 8.5 were the ones below the red line. Okay, so let's try a couple of examples from both of these sections. Let's say we out of this. So to sort of mimic the idea of what might happen when you're at the end of the chapter where you don't really know which of these tests applies, let's look at some converge or diverge problems where we don't really know which of these sections it came from and therefore not necessarily which test to use. But let me grab something from the book. So let's say I have this series. So let me give you guys a minute to sort of just think about this in general. And the thing you want to think about is what kind of a problem is this? What is the goal of the problem? And then how would I pursue that goal? What tools would I use? What tests would I use in this case? Things like that. So I will shut up, but feel free to ask a question if you're working with this, but I'm going to stop talking for a minute. All right, so here's where the rubber hits the road. You're just staring at some series and trying to understand by its formula what it is. So let's consider this. It's often helpful to write out some terms. So for example, this 3 I could factor out front because it's a constant. That's using properties of series. And if I did that, I would have 3 times the summation as k goes from 2 to infinity of just e to the minus k, which is 3 times the summation as k goes from 2 to infinity of 1 over e to the k. So maybe if I write out some of the terms as I was suggesting, this is 3 times 1 over e squared, because we're starting with a 2, plus 1 over e to the 3rd, plus 1 over e to the 4th, etc. So writing things out this way, writing out some terms, realizing that the 3 is irrelevant and just a multiple, maybe that makes it easier to see if it converges or diverges. Can anybody label what kind of a series this is? So I see a couple people say P series, a couple people say geometric, or Wenzel says geometric. All right, so that's what we want to wrap our mind around, these kinds of things. So P series or geometric, let's compare those two, geometric versus P series, see if one of these applies. So geometric means it's something of the form where you keep multiplying by some number r, and we even had a formula for that, where basically a sub k would be whatever the first term is times r to the k minus 1. whereas a P series is something of the form 1 over K to the P. So the thing I would point out about the P series is that the power that you look at in the P series is on K. And if you look at our series, we don't have K to a power. K is the power. So sorry to burst a couple of bubbles there. This is not an example of the P series, because for the P series, the K number that's getting bigger and bigger is raised to some power P. Whereas what we're looking at instead is in this situation where K is the power. And in that structure, this is actually a geometric series. So this is the challenge, to sort of look at these things out of the blue when you've done several different things and try to figure out, well, what am I talking about here? Until I get your eraser. All right, so this is an example of a geometric series, because if you look at what's happening is that each time you're multiplying by 1 over E. You're multiplying by 1 over E each time, so that you had 1 over E squared, then you multiply by another 1 over E and you get 1 over E cubed, etc. So there's a constant multiple of 1 over E each time. So that makes this a geometric series. Our first term, if I'm not counting the 3, is 1 over E squared. And so the sum of the series can be used by using, we could actually determine not only that this converges because this R value is less than 1, so that tells us that it converges, but not only that, we could evaluate this series and determine the value itself, because we have a formula for the geometric series. So that would be that the sum is equal to, I'm going to put it this way, 3 times the sum for what's in here is equal to 3 times, and for the sum we would do A, which is 1 over E squared divided by 1 minus R value of 1 over E. So if I wanted to simplify that a little bit, just to finish with, because it is a problem from the book and we should keep going, I would multiply this by E squared in the top and the bottom to get rid of all of those little fractions. And so I would get 3, in the top becomes a 1, so I'm going to put the 3 up there. And on the bottom, I have E squared minus E. So maybe I'm going to just leave it that way. You could factor it, but there's no reason to. So in this case, not only can we conclude that this series converges, but we can actually find the value that it converges to, because it's a geometric series, and we have a formula for that. So this was actually number 44 on page 638 in 8.4. Questions, comments, discussions about this example? Okay, where are we at? We have like 45 minutes. Okay. So, yeah. Time is precious. Okay, so let's, I'm going to go ahead and look at 8.6 so that we can finish that, and then we can take a break. And then whatever time we have left, we can try to look at all of chapter 9, which is 4 sections. So we just had a bunch of tests. But in all of the tests, the assumption was the series typically, except the divergence series, all the tests, the series assumed that the terms were positive. So in 8.6, we introduced the idea of an alternating series where maybe the terms alternate and sometimes they're negative. And with that in mind, we have this test for an alternating series. So we have a new test, the alternating series test, which is Theorem 818 on page 650. And basically what it said, without writing it out too much, is that if the series alternates, it will converge as long as the terms of the series have magnitudes that are non-increasing, magnitude meaning absolute value. So if absolute value of a sub k's is non-increasing, so that just means that they never go up in value. They could stay the same for a while and then decrease as much as they want, but they never go up in value. And if the limit of the terms is 0, then it converges. So for an alternating series, if you meet these two conditions, then you get convergence. And so the quintessential alternating series that's introduced that you want to keep in mind is the alternating harmonic series. So let's remind ourselves harmonic and then what it looks like when it alternates. So if I have the series as k goes from 1 to infinity of 1 over k, that's the harmonic series, and it diverges. But if we allow this to alternate or cause it to alternate, so I'm going to put a -1 in the top, and so that it starts with a positive, I'm going to put k minus 1 power over k. Then I get 1 minus a half plus a third minus, etc. This is the alternating harmonic series. And it passes the harmonic series test we just wrote out, so this converges. So this is a very, very important pair of series to think about, because they are a quintessential example of how you can have a series which, if all the terms were positive, would diverge, and they would literally have a total that heads off toward infinity. But if you instead set the terms to alternate in sign, then when you add those all up, they actually converge to a value. That instead of going off to infinity for the total settles in on a specific number. And so this set up 3 situations which had a definition that when you have a series, that there's 3 possibilities for an alternating series. So let's write that, maybe I'll write that in blue. So alternating series have 3 possibilities. One, so let's look at this example that I'm showing right above, the alternating harmonic series. So I'm going to write the alternating version converges, but the absolute value version, meaning if all the terms are positive, diverges. So if the alternating series version converges, but the absolute value version diverges, then we say this is converges conditionally. I think I am out of space or no? Yes. So that's situation 1. And so we are using these situations to define, two things, converges conditionally or converges absolutely. So option 2, and I'm going to have to erase it. Maybe I can try to fit option 2 on here first, at least. Option 2 is that the alternating version converges and the absolute value, meaning all positive terms version, also converges. So what that means is, unlike the harmonic series, you didn't need to make the terms alternate in order to get convergence, because when they were all positive, they converged anyway. So a good example of that is a convergent geometric series. So if I have 1 over 2, 1 over 4, 1 over 8, I have a geometric series it's going to converge if all the terms are positive. Well, if I then turn around and make them alternate, it's still going to converge. They're going to be less of a total. So then you may recall that we say that it converges absolutely. So it converges absolutely if the absolute value of the series is a series that converges. And so then, since I'm sort of out of space, number 3 is when you have an alternating series that diverges instead of converging. So there's three possibilities. First, that the alternating series just diverges. It never settles on a value. And then the other 2 possibilities are both where the alternating version converges, but the absolute value version either converges or diverges. So if they both converge, then the alternating convergent series converges absolutely. But if the alternating one converges while the absolute values would then create a divergent series, then we say that the alternating series converges conditionally, because its convergence is conditional upon the fact that the terms alternate. So we set up these definitions and we looked at these examples, and it puts us in a position for a theorem, which is basically going to be how we deal with most alternating series. So let's just finish by reminding ourselves of that, try to squeeze in an example, then take a break. So then the crucial theorem for the alternating series section, let me see which one it is. Where is it? 821, theorem 8.21 on page 654. And it basically says that absolute convergence implies convergence. So what that means is, if you have an alternating series and you don't know if it converges or not, then you can consider, instead of using the alternating series test, you could just say, well, what if all the terms were positive? And if you can determine that when all the terms are positive, that series converges, well, then you have a situation where the series is absolutely convergent. Since all of the terms positive gives you convergence, then the series, when it's alternating, must also converge. So if the series of absolute values converge, then this alternating version must also converge. And so that basically, when you have an alternating series, you're probably just going to use all the tests that we've usually used in the first place, ignoring the alternating aspect, and try to get convergence that way. And if you're not able to get convergence that way, then you probably turn to the alternating series test for convergence, like we had to with the alternating harmonic series. Anyway, those are the ideas. So let's squeeze in an example, and then we'll take a break. Yeah. So let's try, maybe it's on page 657, number 21. So it says, alternating series, determine whether the following series converge. So it has -1 to the k. One plus 1 over k. So we could maybe write out a couple of terms here to try to see what's going on, but pretty quickly, that may or may not be helpful. Pretty quickly, we're going to have to do some sort of a test or something. So if k is a 1, then I get a negative because -1 is raised to an odd power. And then I get a 1 plus 1/2 here. So this becomes -3/2. When k is a 2, then this becomes +1. And so I just get 1. Oh, that was a mistake already. When k is a 1, I get a negative, but I just get 1 plus 1, which is 2. So this starts with -2. Then when k is a 2, I get a positive and 1 plus 1 over 2, which is the 3/2 that I just was saying. When k is a 3, I get a negative, and then I would get 1 plus 1/3, which is 4/3, etc. So since time is short, I will just point out that what you could envision here is if I ignore this initially, so I'm kind of thinking about the absolute value version of this series, and I'm thinking about what happens as k gets bigger, this fraction here is going to go to 0. But I still have this 1 sitting here. So basically, this then tells me that the limit as k goes to infinity of these terms is not equal to 0. So this diverges by the divergence test.